Two 8 mm thick plates are placed 5 mm apart and welded by a butt joint. Welding is carried out at 20 volts at a speed of 5 mm per second. Heat transfer efficiency is 0.8 if the heat required for melting steel is 10 joule per mm cube and melting efficiency is 0.625. The weld current will be. Here generally the heat required is given by I square RT or VIT. So here T is the time for welding, time required for welding, and I is the current required, and V is the voltage. So here, and the efficiencies are given as heat transfer efficiency is given as 0.8 and the melting efficiency is given as 0.625. But it is mentioned that the heat required for melting steel is 10 joule per mm cube. So that is the total heat required is equal to real heat required is equal to 10 joule per mm cube into the volume of the weld bead. So here there are two 8 mm thick plates are put at 5 mm apart. Okay, and these are the 8 mm thick plates, and here we will have to find out this area and this volume, but we don't know the length of the bead. So let us say the volume of the weld is 10 joule, 10 into 5 into 8 into L, so it is equal to 400 L, so joule. Now consider the equation VIT. So from this here Q is equal VIT, V voltage is given as 20 and into I into the time required can be calculated by using the length of the weld to the speed of the weld, that is L by 5, which gives the time required for welding it, and is equal to 0.8 into 0.625 is equal to 400 L. So here LL get cancelled, and from this equation we can calculate I, the current required to weld is equal to 200 amps. So in options, the right option is B. Sales for an item is 10,000. The ordering cost for procuring the item is 25 rupees per order. If the carrying cost amount to 12% of average inventory, then the number of orders per year is. Here it is given that annual demand is equal to 10,000 and ordering cost is given by 25 rupees per order, and here the carrying cost or inventory cost is equal to 12%. So we know that the economic order quantity is equal to 2A C naught by I and is equal to 2 into 10,000 by 25 by 0.12. So which is equal to 20.42. Now the number of orders per year is equal to A by EOQ, so which is equal to 10,000 by 20.42. Sorry, it is 2042, 2042, and here it is also 2042, which is equal to nearly 4.9 and is nearly equal to 5 orders per year. So in the option, the right option is B. The plant has a capacity of producing 50,000 units per year. The annual fixed cost is 90,000 rupees. The variable cost per unit is 18 rupees. The price of the product is 20 rupees per unit. Then the break-even point in terms of the capacity of the plant is. So here already the capacity of the plant is given, that is 50,000 units per year. So we will have to find out the break-even point, and then we'll have to take the percentage of the break-even point with capacity of the plant. Here break-even point is given by fixed cost by price of the product to minus variable cost. Here fixed cost of the annual fixed cost is given as 90,000 rupees and price of the product is 20, and here the variable cost is given by 18 rupees. So by using this we can have the break-even point is 45,000 units per year, and the percentage of the break-even point with respect to the capacity is equal to 50,000 minus, sorry, here it is 45,000 by 50,000, so which is equal to 90%. So in the option, the right option is D. D is the right answer. An element in pure shear is subjected to a shear stress of 50 megapascal. Here it is a common data question. It consists two questions. The data is given just in a line, that is an element in pure shear which is subjected to a shear stress of 50 megapascal. The maximum and minimum normal stresses induced in the element are, and here the options are 25 megapascal minus 25, 50 and minus 50, 0 and 0, 50 and 0. And the second question is the maximum shear stress plane orientation to the zero shear stress plane is. So coming to the solution, first draw a Mohr circle for a given problem. Here the element is subjected to pure shear only. Take shear stress on y-axis and normal stress on x-axis. Here the element is subjected to a shear stress of 50 megapascal. Now consider on both the sides of the y-axis a magnitude of 50 megapascal. Now take the center between these two and take the radius of 50 megapascal and draw a circle here. So it is nothing but Mohr circle, and here this is the maximum normal stress and this is the minimum normal stress, and here this is equal to the radius of the Mohr circle here. So that is nothing but 50 megapascal, and in this case also it is 50 megapascal. These two are called maximum and minimum principal stresses, or we can say that the maximum and minimum normal stresses. So here it is the magnitude is 50 and direction is positive, and here the magnitude is 50 and direction is negative, so that the maximum and minimum principal stresses are 50 and minus 50. So in the option, the right option is B. So coming to the second question, the maximum shear stress plane orientation to the zero shear stress plane is. Here see, this is the maximum shear stress plane, so and maximum shear stress occurs at this point, and this is the minimum shear stress plane, that is zero shear stress plane. So in between these, the angle between these two planes is 90 degrees. So but we know that the angle made by the two planes on the Mohr circle is double the actual angle made by the planes in the actual member, so that the actual angle is equal to half of the 90 degrees, that is 45 degrees. So the maximum shear stress plane orientation to the zero shear stress plane is 45 degrees.